All right, here we go. Okay, yesterday we started talking about how we can add up areas under curves. That's right.
You start your summer wardrobe?
I did. Yes, I did. So, okay, remember what we did? We looked at some ways we could approximate the area under the curve, and we decided you guys came up with this. It was a great idea using rectangles because they're so easy to work with, right? Calculating the area of a rectangle is an easy thing to do, right? So here's our goal then. What we want to do is come up with an organized way to add up the area under a curve from some lower limit, which we're going to call A, to some upper limit, which we're going to call B. Okay? And to do that, we decided we would just cut the function into slice it vertically into pieces, right? So we'll go, there's a slice, oh, that's not what I want to do. I want those. That's what I want. Okay. So, let's just go there, etc.
Those are actually pretty professional.
Yeah,
You got it.
that's teacher college. That's the kind of stuff I learned how to do.
You are. I was so impressed.
Jolie,
Oh,
it's just so simple. It's almost like there's not even any challenge anymore.
I think you can't have a baby.
Yeah, etc. Right? So here's what we're going to do. We're going to cut this thing up, and we want to add up these areas, right? So in order to do this, let's go ahead and first of all, let's decide how thick our intervals, how wide each slice is going to be, right? Let's just say that we want to cut this into, arbitrarily, let's just say we want to cut this into n subintervals. And we're only looking at the area on the interval from x equals a to x equals b, right? So if we're going to call delta x the width of a slice, how am I going to define that in terms of a and b and n? What if I had, for example, a 24-inch sub and I wanted to cut that into eight equal pieces? How wide would each piece be? Total length divided by the number of pieces, right?
Yeah.
Okay, so we're not talking about subs. It's after lunch, so that's fair game. We're talking about an abstract curve, but the idea is the same, right? If we want to know how wide each piece or each slice is going to be, we're just going to take the total width, which is just b minus a, right? Divided by the number of slices n. Okay, so if we call delta x the width of any subinterval, it's just b minus a over n, right? Okay, so then how could we label? We want to in an organized way, we want to be able to identify the x value of each of these, the left and right edge of each of these slices. So the first one is going to be what we might call x sub 0, and that's just plain old a, isn't it? Right? That's our 0th slice. Thank you, Stephanie.
She went to the bathroom.
Oh, okay, so she'll be back. Is she right here? Right there? Okay, hang on, hold up. Shh, hang on. So if we want to, we're going to call this x sub 1, right? I'm going to do one thing here that might be useful. Let me. How straight those are, Julie. She just left. Oh, she did. So that's x sub 1, right? That's going to be the right edge of the first slice. X sub 2 is going to be the right edge of the second slice, etc., right? That's x sub 3. Okay, I'm going to call this, so this is slice number 1, slice number 2, slice number 3. This one we're going to call slice number I. Okay.
We don't know how many
Right, because we want to, I is going to be our index variable, because we want to be able to do here, and we do this a lot in math, and this will remind you of last year probably a little bit when you did your discrete math part of pre-calculus. We want to be able to define whatever it is that we're incrementing. In this case, it's going to be a slice of our area. We want to be able to just be completely random and generic about that. So we're going to say that for I, right, for number I, which could be anything from 1 up to n, we want to be able to define what the area of that slice is going to be, right? So if that's I, then this is going to be x sub I, right? And this is going to be x sub I minus 1, isn't it?
Yeah.
So if I is 20, then that would be x sub 19, and that would be x sub 20, for example. Okay, make sense? And then up here, we'll say this is going to be the nth slice. That's the last one, right?
Yeah.
So what's that one going to be? N minus 1. And that one's going to be n minus 2. Good. Okay, so then if we kind of work our way backwards, this is x sub n. That's x sub n minus 1, x sub n minus 2, x sub n minus 3, etc., right? Okay? So if we wanted to, for example, come up with what we might call an upper sum, we want to come up with the sum, because we have a monotonically increasing function, we want to come up with the areas predicted by the circumscribed rectangles. So the ones that we're pushing down from above, right, that enclose the function. Does that make sense?
Yeah.
Okay? So then that's going to look like these, right? Right. Those are going to be the tops of the.
Yeah.
Okay. Okay, agreed? So we ought to be able to add these things up then, right? It's just we know that we're just going to have, if I look at the ith one here, I could just take a sum of all the areas of the ith interval as I goes from 1 to n. Agreed? Okay. That looks like a good proposition, right? So we could say, now what is going to be the area of this rectangle? The area of a rectangle is easy to calculate, so I'm going to call this A sub I for the area of the ith slice, ith rectangle. Okay, what's the height going to be? What's the height of that rectangle going to be? Given that this function is just f of x, let's say. Okay. How do I determine the height? Say it again. Okay, so f of x is giving us the height, isn't it, right? But the height of the rectangle is determined by the value of the function there, right? At what x value? X sub I. Does that make sense? Okay. So a sub I then is just going to equal f of x sub I, right? That's the height, times what's the width going to be? What's the width of each one of these?
1 n x.
Delta x, right? Because that's what we said, right? This is, if we have n subintervals, then that's what delta x means. Delta x is the width of each slice, we'll just call it, right?
Yeah.
Okay, so this is delta x, and so we just get that, right?
And we could substitute.
Yeah, and so really all we've got to do then, if we want to come up with the total area of the circumscribed rectangles is just going to be the sum of a sub I as we sum I from 1 to n, right?
That's the E.
Yeah, that's a sigma, right? Remember that from last year? That just means a discrete sum. We're just going to add up of sum of terms. Okay? Okay. So, okay, so that looks good, except the only problem we have here is x sub I. Everything is pretty good there. Presumably, we'd be given the function that we're working with. But what is x sub I going to equal? We've got to be able to write x sub I in terms of stuff that we know, right? X sub I is pretty abstract. Think about what x sub I is, though. X sub I is where we end up if we start at x sub 0, which is just a, and we incrementally move to the right, how, like, I steps, you can think of, right? Of what width is each step. So it's like I'm gonna start there, I'm gonna step there and there and there, all the way up until I get to there. I've taken I steps to get there. How wide would each step be? No? Delta x, right? Because that's the width of each slice or each subinterval, right? So I'm going to start at the left-hand edge of my big interval, and I'm just going to step over incrementally delta x I times to get to x sub I, right? So does it make sense then that we could say, okay, then x sub I is really just a plus I delta x, right? Does that make sense?
Wait, why would A? Okay.
Okay.
Why I?
Because we're looking specifically at the ith rectangle.
Oh, so
Okay.
instead of being like 2, like the first ones are 1, 2, 3, you're going.
Right, but what our goal here is everybody kind of get an appreciation for why we're doing this. We want to be able to say, okay, if I could define exactly what the area of the ith interval is, well then I could I could specifically add up the area if I had a value of like 2 or 4 or any discrete value, right? I want to come up with a formula that's going to allow me to predict the value of the area of the ith rectangle based on the value of I, right? Okay, so if I is 7, then this would tell me that whatever A is, let's just say hypothetically that A is 3. Okay, what if it's 3? Then x sub I would equal 3 plus I times delta x. But delta x is actually going to be a number, right? It's going to be a number because it's going to be the width of the whole interval, which is something we're going to know, right? If the upper limit is 13, let's just say, then that's going to be 13 minus 3, so that's a width of 10, right? 10 divided by however many slices I want. If I want 20 slices, then that would be 10 divided by 20 is 1/2. Delta x would equal 1/2 in that case, right? So delta x is going to be a number that we know, right? And so we'd end up with, in this case, x sub I equals 3 plus 1/2 times I, right?
But we still don't know right?
Well, but I has to be able to be lots of things because I is our index variable.
Okay.
And we're going to be able to add up the whole thing by just saying, okay, well, let's add up the area of the ith interval as we let I walk from 1 to n, right? And really all that means is just a sub 1 plus a sub 2 all the way out to a sub n, right? Okay. All right, so then that allows us to make this a little bit better then. That means that the area of the ith interval we can now write as f of a plus I delta x times delta x, right? And so what if our function is like x squared? Well, that's okay. Then we would just have a plus I delta x squared, right? Get the idea? Okay. So we can come up with then the total area is the sum of this, f of a plus I delta x times delta x as I goes from 1 to n. Yes?
Okay, so, like, I know you can do this different percent calculator, but if you want to do an infinite number of slices, like, how do you put that in?
Okay, yeah, you can't really do that. You can do it on a TI-89, but you can't really do it on a TI-83. But we're not going to have to. We'll see something that'll. So if we wanted to, for example, let's say we want to add up the area under the curve. I'm going to give you a specific one. Let's say,
So would that be our general formula when we get a problem like this?
well, this is the formula for the circumscribed rectangles, right? The inscribed rectangles, what would that look like? Before we do anything else, let's look at that. So this is, we'll call this capital A. Let's make lowercase a be the smaller area, the area of the inscribed rectangles, the one that we're pushing up from the bottom, right? So that would be the sum of f of what? Okay, so it's going to be the same kind of thing, only this time, this is what they would look like, right? They would have the red heights instead of the blue heights. And so that would be the area of the ith inscribed rectangle. Well, the only difference is that we're calculating the height of the rectangle based on this x value instead of that x value, right? So really the only difference here is just that this would look like f of a plus, instead of an I, it's going to be an I minus 1 times delta x, right? Unfortunately, that makes the math a little bit more cumbersome, okay? But remember the trick that we played yesterday, and I want you to keep this in mind. The trick we played yesterday eventually was busted. Yeah.
Oh, I skipped, we just talked with him about, like,
The
pictures of
report.
passing subs.
Oh, I got it.
And how effort is right.
If you're gonna graduate and all that
Also,
stuff.
yelling at all of us for physics, but you never fix it.
Oh, I did fix them. I fixed them yesterday.
They're all F's.
What's that?
They're all F's.
No, I fixed them
So
yesterday.
he's like, why do you have an F in physics? And I was like, because Oya never updated them.
Thanks for throwing me under the bus. I appreciate that. That's good. That's good. So
Speaking of grades, have you corrected the tests?
Yeah, have you done a written test, like the ones we
The rewrites,
retakes?
retakes?
I haven't. I'll do them ASAP. There's still people taking them, but I'll just try
I
to do
thought
it
you said
once a
today
day.
was supposed to be.
Was what? No, I'm gonna let people take them through the week. Yeah.
Right, can you start correct?
Yes, I'll start correcting.
Maybe
Yeah.
some earlier, I was gonna take
Okay, so I want you guys to think back to calculus though. Think about the trick we played, like with the circle, right? We said that we could get the exact area of the circle if we let the number of sides of the regular polygons that circumscribed and inscribed it go to infinity, right? And I don't know if I don't think I kept that one. Remember what that looked like? We had like a regular polygon on the outside, and then the circle, and then a regular polygon on the inside. In the limit that we let the number of sides go to infinity, the top one gets smaller and the inscribed one gets bigger, and they trap the exact area of the circle, right? So what's going to happen here? If I were to let the number of subintervals get really big, what's going to happen to this? What's going to happen if I let the number of subintervals get really large?
That area gets smaller.
Will be less possible.
It's going to be more precise, isn't it? In fact, I think I've even got, hang on here a second, let me find something. Highlights, I just leave out sometimes, that's not good. It's all a highlight though, really, isn't it? So,
What are you talking about?
the highlights of our little talk here. I didn't film that last part. Okay, so which one of these do you think would be easier to work with?
The first one.
The first one, right? Well, why would we not just use the first one if ultimately we know that our strategy is going to be to let the number of subintervals go to infinity anyway? Pick the easiest one, right? Okay, so we would. We would just settle on that one, right? We're going to make one little change to this, and then this looks like, well, okay, so let's go to the next page for a second.
So is this still the stuff that we're not going to test on? This just the stuff that we're going to
Yeah.
And if this is if we take a calculus class to college after this, or if we take like
Calculus. Yeah, this is calculus. Okay, so let's do one of these. Let's actually go through the process of calculating a discrete sum, and then we'll talk about how we can do calculus trickery and find the exact area. Okay? So what if we take the function f of x equals, we'll just make it x squared, how about? F of x equals x squared, and we're going to do this on the interval from 1 to 3. And let's say we're going to use a total of 15 slices. Okay? So what's this look like then? So what's our delta x going to be? Delta x we said was just b minus a over n, right? Well, b is, what's a and what's b?
3 and 1.
3 and 1. Okay, so a is 1, b is 3. So this just looks like 3 minus 1 over 15 equals 2/15.
I wasn't here for this, but why can't I just call X and Y? Because that's what they are.
Well, because x and y are variables, and these are just the edges of the area of the interval that where we're adding up area.
No, but I mean like the A and B, but because those are on our axis, 1 and 3 are X and Y.
No, right, they're both x values, because you see what they are is just, this is A and that's B, so we're adding up this area, right? We're adding up the area. Okay, does that make sense?
Yeah.
Okay.
Okay. That
Okay.
What?
Oh, I got some in the other room. Okay, so there's delta x, okay? A is 1, B is 3, our function is x squared, so we can add this thing up now, right?
Yeah, we can.
So our area then that we're looking for, we'll call it A sub 15, right? So the area for 15 subintervals is going to equal the sum of f of 1 plus I times delta x. Well, delta x is 2/15, so isn't that just 2I over 15 times 2/15, right?
Yeah.
As I goes from 1 to 15. Okay, and f of x is x squared, so what's f of hand? Hand squared, right? So we get the sum of the quantity I plus 1 plus 2 I over 15 squared.
So is I just a general?
So I is what we call an index variable,
Wait, where did you get the squared from?
because
Okay.
f of x, right?
What's an index variable?
Well, so whenever we do discrete math like this, when we're doing using sigma notation, we're adding up a discrete sum, then we have to keep track of, we're going to add up a certain number of those, but we got to keep track of which one we're adding up at a given time. Okay? So this is something that we could do in a number of ways. Probably the easiest would just be to put this in our calculators and get an answer. Okay? If we had more time, I would show you how I could give you I could show you some stuff like this. Like, for example, the sum of I squared as I goes from 1 to n is n times n plus 1 times 2n plus 1 over 6. Just for example. Is that right? Yeah, that's right.
And that, sorry, the bottom equation of x squared is because your function is x squared.
is
Yeah.
yes. Mm-hmm. Did I get that wrong? I think this is yeah.
So if we have a function like,
Is that right?
we're not gonna have functions that are like square root of.
No, I'm not even gonna make you do these because it's not that useful.
Oh, okay.
Yeah,
And
that's
so
right.
that bottom one would be our answer.
So this would be what I'm saying is we could actually come up with this without a calculator, right? Because if I were to, this 2/15 is a constant, so I could pull that out in front of the sigma. You might remember that stuff from last year, right? You can always factor out a constant.
Yeah.
And then we could expand this thing out, and we're not going to do this, but what we'd end up getting is 2/15 times the sum. I'm not going to write the whole, just when I say sigma, I just mean all that stuff, right?
Yeah.
Okay. So the sum of this thing squared, right? If I square that out, I'm going to get 1 plus 4i over 15 plus 4i squared over 15, over 225. Okay. If I squared that out. Okay, that's what that stuff would become if I squared it, right? So if I separated that into terms, I could just add up the sum of 1 from 1 to 15 plus 4/15 times the sum of I plus 4 2/25 times the sum of I squared. All those things are just numbers that we could use. I mean, I could show you what those are. For example, the sum of I as I goes from 1 to n is n times n plus 1 over 2.
That the calculator would give us that?
Well, yeah, I mean, I could give those to you, and you could do the algebra. I'm just telling you, that wouldn't be a big deal. I mean, if we had more time, I'd probably make you do a couple of those, just to get the practice of doing it. But it's not that big a deal. You can also just let your calculator do it, and here's how you can put this in your calculator.
I already took it.
Do you know how to do it?
Yeah, I did it.
Okay.
And that's the
So you guys, you've done this last year, right? So you know how to put these in your calculator?
No, we didn't
No,
do it
I
last year.
forgot.
Oh, well then I'm going to show you.
Yeah, I figured it out, but.
We did it for you.
Yes.
Is that n a plus 1?
This is supposed to be an A. You don't even have to, Julie, you don't even have to write this down. It's not, that's not even worth writing. No. Say it again. So the I means, here, I'll